My name's Frank, and today I'm going to be presenting Bundler, which is a new system we've built for enabling traffic control between different sites across the internet. So what do I mean by that? Well, first, by a site, I'm broadly referring to any single physical location where there's many different endpoints sharing the same access link to the internet. So some common examples of this would be a university campus network like MIT, a company office network, or even a particular data center from a cloud provider like Amazon's US West data center. So let's start with this company office network as a motivating example. Imagine you're the network administrator for this company, and there's a lot of different people and applications using the network, each with different requirements. So there's SSH traffic and interactive web browsing that need low latency. There's cloud storage and backups that need high throughput. And then there's video streaming and Zoom calls, which need a mix of both. Now, a common problem you might encounter here is that every time Bob runs a backup session, Alice's SSH traffic starts lagging, or her Zoom calls get choppy. So what might be going on here? Well, as everything is shifted to the cloud, all of these different applications typically have an endpoint in one of just a few sites. So either a data center from one of these major cloud providers like Amazon or Google, or maybe another site of the same company. So it's possible that Alice's SSH traffic is going to an EC2 machine, and that her Zoom call and Bob's backup traffic are hosted in the same Amazon data center. Since these connections are all going to the same destination site, even if they're different physical machines within that site, they're likely taking the same path to the network and thus sharing the same bottleneck as well. And if that's the case, then wherever this bottleneck is, the queue probably looks something like this. So the backup has plenty of packets to fully occupy the queue, and the latency-sensitive applications are always stuck waiting behind it. Now, as the network manager, if you saw the situation, the natural solution would be to implement some sort of scheduling policy. So for example, your policy in this case might be to give highest priority to Zoom calls and SSH, and then only send backup traffic when there's no other packets waiting. And this sort of scheduling is what we mean by traffic control. So if this bottleneck is occurring somewhere inside your own network, then you could just stick a scheduler here and call it a day. But a lot of recent work has shown that today, bottlenecks are often somewhere beyond our network's edge, for example, at a slow or congested interdomain link. And if that's the case, then this queue will actually build at the bottleneck in the middle of the network instead, meaning the queue back within our site will be relatively empty. And if our queue is empty, then there's no packets to schedule. So putting a scheduler here isn't going to really do anything. Now, naturally, you might wonder, why not just have scheduling in the middle of the network if that's where bottlenecks frequently occur? Well, first of all, of course, many people share the public internet, and there isn't a one-size-fits-all scheduling policy. Each site might have a different set of traffic they want to prioritize or deprioritize. And this traffic is traveling between many different parties along the network path, different ISPs and autonomous systems, and the bottleneck could occur anywhere. Maybe it's at this link, or this link, and so on. So to ensure your scheduling policy is always enforced, you'd have to coordinate with every possible provider along the path and convince them to apply your policy. So let's take a step back here for a minute and just summarize the problem so far. You have a bunch of traffic going between your site and another site, and you'd like to enforce some policy about how that traffic should share the limited network resources. Now, no one in the middle of the network can implement that policy for you. It really makes the most sense for you to implement the policy yourself, since you know your own traffic best. But when the bottleneck is outside of your network, you don't have a queue to schedule. So what can you do? Well, if we need packets in our queue to schedule, but they only build up at a bottleneck, then one thing we could do is artificially create a bottleneck within our site by putting our traffic through a rate limiter. As long as we choose a rate that's less than the real bottleneck, our rate limiter will become the bottleneck. And as a result, our traffic's packets that would have queued at the real bottleneck shift and queue at our rate limiter instead. So now we have packets in our queue and we can implement scheduling. But how do we pick the right rate? Let's put some numbers here as an example just to make things more concrete. So suppose the real bottleneck link is 10 megabits per second, and that our company's uplink to the internet is something much higher than that. Now, if you rate limit our traffic to anything less than 10, we will build a queue, but we'll waste bandwidth because the network could have supported up to 10. If we send anything more than 10, we won't build a queue at all, so we'll be right back where we started, unable to schedule. So to maximize throughput and build a queue, we want to send at exactly 10. But of course, life isn't so simple. We don't really know that the bottleneck is 10, and it's not static. It's going to be changing constantly as network conditions evolve. So imagine, for example, that all of a sudden there's some other traffic sharing this link that averages 5 megabits per second. Now, if we keep sending at 10, our packets will go back to queuing in the middle of the network. In this scenario, we'd actually need to send it 5 in order to maximize throughput and still build a queue back within our own site. So this sort of seems like a dead end. How can we possibly know the right rate, given there's all these different possible scenarios? Well, if you tilt your head a little bit, this is actually a very familiar problem, right? Determining the available bandwidth in the network at any given time is exactly what congestion control aims to do. And this is the key idea behind bundler. So bundler is just a middle box that sits at the edge of a site. And internally, it has 2 components. There's a sendbox that observes all of a site's egress traffic, and then a receivebox that observes all of its ingress traffic. Now, the sendbox groups egress traffic by its destination site, and it treats all flows going to the same destination as a single aggregate stream of packets, which we call a bundle. Now, the set of traffic going to this Amazon data center we've been looking at so far would be one example of a bundle, but then we might have another bundle for all of our traffic going to a Google data center, and then one for our Dropbox data center, and so on. Now, each bundle has its own queue and its own rate limiter within the sendbox, and bundler operates over them independently. So for each bundle, the sendbox is going to use congestion control to pick an aggregate rate for that bundle that will cause the queues to shift without sacrificing on throughput. And then the scheduling policy will decide how that aggregate rate is distributed among the flows. Since picking the right rate is key to bundler achieving its goal, let's take a closer look at how it's implemented. At a high level, congestion control just involves measuring some signals about the current network state, things like the RTT, the receive rate, and then using these signals to adjust the rate traffic is sent to achieve some objective. So let's start with the measurement aspect. Traditionally, a TCP sender computes measurements for congestion control using the acknowledgements sent by the TCP receiver. For example, to calculate the RTT, it compares the time it sent a packet to the time that packet is acknowledged. And it does this independently for each TCP flow. In contrast, the set of packets in a bundle correspond to many different flows, and while some of them may be TCP, many applications in the bundle will use other protocols, such as UDP, which doesn't have acknowledgements, or QUIC, where the relevant header information is encrypted. So to measure across all traffic in the bundle, we need a mechanism that can provide feedback for all different kinds of protocols. Now, the most common approach to solve this would be to transform all the traffic to TCP using a TCP proxy. The way these work is that the proxy servers terminate the connections, meaning the endpoints connect to the proxies instead of each other directly. And then the real data packets are sent across the network over a pool of persistent TCP connections between the proxy servers. Now, technically, this is a viable design. We could use the acknowledgements from the proxy connections to do congestion control as usual, but it introduces a lot of extra complexity and overhead that it turns out is actually unnecessary for our goal. The main issue is that by terminating connections, the proxy takes responsibility for the packets. So, for example, to implement TCP reliability, it needs to hold on to all the packets until they're acknowledged. If any packets get dropped between the proxies, it's the proxy's responsibility to retransmit them, not the endpoint. So it needs to maintain state for all of these. Since bundler is dealing with an entire site's traffic, this could actually end up being a significant amount. And then if either side of the proxy goes down, all of the existing connections will be dropped. The network may be able to route around it for new connections, but any existing connections will be stuck, so it doesn't preserve fate sharing. So to simplify the architecture, we instead leave the connections intact. The send and receive box simply forward the traffic along without changing it. But the receive box sends acknowledgements back to the send box out of band from the data packets. Now, we could have the receiver send feedback for every single packet, just like in TCP, but that would create a significant overhead. Again, the send box would need to maintain state for every packet until it's acknowledged. And the receiver would need to send a lot of extra packets on top of the existing ACKs that are already being sent between the endpoints. Fortunately, this isn't necessary. Congestion control operates in the time scale of an RTT, so we really only need to sample the network conditions roughly once per RTT. Now, one simple way to do this would be for the sender to sample a packet per RTT and then mark a bit in the header so that the receiver knows which packet to send feedback for. But of course, changing existing packet headers to incorporate a new field would be impractical. So instead, we developed a scheme that allows the sender and receiver to sample the same packets independently without modifying them at all. The main requirement for this scheme is that there exists a set of fields in the packet headers that can be used to identify packets uniquely over short timescales, and that won't be modified between the sendbox and receivebox. Now, the particular set of fields that work best will depend on the deployment scenario, but as an example, in our implementation, we use a combination of the destination address and the IP ID, which are in the IP header of all packets regardless of transport protocol. So to see how the scheme works, let's take a closer look inside the sendbox and receivebox. Now, the bottom of each box here represents the data path, which observes a stream of all the packets from all flows in the bundle. And then the top box represents the control plane, which is off of the data path in user space. Now, for each packet that flows through the sendbox, it hashes the set of header fields that we talked about earlier. And whenever this hash is a multiple of the desired sampling rate, it stores some information about that packet in the control plane. So for example, the time the packet was sent. So let's call this packet we just found X for now. And let's suppose that it was sent at time T1. Now the receive box does the same thing for each packet. It hashes the set of header fields and it looks for a packet that's a multiple of the sending rate. So at some point later, it's going to observe this same packet with a hash of X. And when it does, it sends a feedback message back to the sendbox, including this hash and again, some other statistics. When the sender receives this feedback, it looks up the hash in its table of sent packets, and then it uses it to compute a set of measurements. It feeds these measurements to the congestion controller, which then computes a new rate for the bundle. So just as an example of how these measurements are used, if we received the feedback message for hash X at T2, then a sample of the RTT would just be T2 minus T1. Now we use the feedback to compute a number of other signals, such as the send and receive rate, and the details for doing this are included in the paper. But there's two important properties about this design that I want to highlight. The first is that it's lightweight and low overhead. Notice that we only needed to compute a single hash per packet in the data plane, and all of the other functionality operates off the data plane. And we also only need to send a single feedback message per RTT, as opposed to the amount of feedback scaling with the rate of traffic. Second, it's totally transparent. Since we're leaving the connections intact and not modifying the packets at all, we're not interfering with the end-to-end connections. So if bundler goes down on either side, the connections won't be disrupted. And it's incrementally deployable. So if there isn't a bundler on the other side, then no harm is done, and the packets can still reach their intended destination. So now that we have the measurements necessary for congestion control, the second question is, which algorithm should we use to pick the rate limit for the bundle? Now, in order to shift the queue to our site, we need to use a scheme that will intentionally limit queuing at the real bottleneck. This points to some sort of delay control scheme, such as COPA, as opposed to a buffer filling scheme like TCP cubic that would seek to completely fill the queue until it sees a drop. Now, unfortunately, it's known that these delay control schemes lose throughput whenever they compete with buffer filling traffic. If this buffer filling traffic is long lasting, then sacrificing throughput in the long term would actually outweigh the benefits of scheduling. So to address this, we use a recent mechanism from our group called Nimbus, which superimposes over top an existing congestion control scheme, and then reinterprets the congestion control signals to measure whether or not any of the cross traffic is buffer filling. Whenever Nimbus detects long-lasting buffer filling cross traffic, Bundler temporarily disables its rate limiter and allows the bundled traffic to compete with the cross traffic as it would have normally. This gives up the ability to schedule, but it ensures that the bundled traffic achieves the same throughput in aggregate that it would have without bundling. Once Nimbus detects that the cross traffic is left, we re-enable the rate limiter and we regain the ability to schedule again. Now, in reality, we don't completely disable the rate limiter. Nimbus actually requires a small amount of queue to be kept at the bundler in order to continue running its detection mechanism. So we actually turn up the rate limit just enough that we maintain this queue without decreasing the overall throughput. Now, there's more details for exactly how we do this in the paper, but what I want to point out is that our ability to switch modes here between enabled and disabled is a key benefit of our measurement scheme. Since our measurement scheme is totally transparent, Bundler can safely disable and re-enable itself in this scenario. If we were using an approach that modified the traffic, such as a TCP proxy instead, this type of thing wouldn't be possible. Now, while this prevents Bundler from causing any harm in the worst case, it does beg the question, how often will Bundler be useful? Well, in order for Bundler to actually disable, the cross traffic needs to continue to fill the same bottleneck as Bundler for an extended period of time. While many flows in the internet use schemes that could fill buffers, such as cubic, most flows are actually short-lived or bursty, which means that in aggregate, they may occasionally constitute a significant amount of traffic, but they aren't individually contributing enough to continually keep buffers full. So in these cases, Bundler's delay control scheme can dynamically adjust to the available bandwidth. Whenever the small flows occupy a large amount of the link, the scheme will temporarily trade a short-term reduction in throughput to keep delays low and retain scheduling abilities. It's only when this traffic is long-lasting that Bundler will actually end up disabling itself, and it's only in this case that Bundler is no longer useful. While we can't provide a definitive answer for how common this is across all links on the entire internet, I can say confidently that all of the experiments run by our group, both for this project and a variety of other projects, indicate that such cross-traffic is rare. So we believe that in most cases, bundler will be able to provide good benefits. So now I want to show a controlled experiment that demonstrates the type of improvements bundler can provide. For this experiment, we created a situation like I talked about at the beginning. We have a variety of traffic between two sites that's competing at a bottleneck in the middle of the network. And this bottleneck is outside of the sender's control, so it can't schedule the packets. To emulate a realistic set of traffic, we generated flow sizes according to a distribution that KIDA observed at an internet backbone router. So this is representative of what you might expect to see in the middle of the network. Now, just to give you an idea of what this distribution looks like, the vast majority, 97.6%, are small flows, each less than 10 kilobytes. And then about 2% are medium flows, and about 0.1% are large flows. And then we looked at the distribution of flow completion times separated into these three different traffic sizes. And what I'm actually plotting here, the slowdown, is really just the FCT normalized by the size of the flow to account for the fact that larger flows will always take longer to complete than shorter ones. Now, the first result we have here is our baseline. Since we're not running bundler, this is representative of the status quo you'd expect to see today. And the main thing I want to point out is that the short flows, which should be able to complete in a single RTT, are taking almost twice as long at the median and more than 4 times as long at the tail. So the ideal solution in this case would be to have a scheduler right at the router where the bottleneck is occurring. Now, as I mentioned earlier, it wouldn't make sense to do this in practice, but it does give us a reference for the optimal benefit a scheduler could provide in this case. So we added the scheduler here, and we configured it to use a fair queuing policy to prevent short flows from waiting behind longer ones. Now, if we look at the results, all flows tend to complete faster, both at the median and at the tail, but in particular, all of the short flows are completing as quickly as possible. So with these as reference points, finally, we removed the scheduler and instead enabled bundler at both sites, configured to use the exact same fair queuing policy. And what we can see here is that relative to the status quo, bundler is able to reduce the slowdown of all flows across the board. And if we look at the short flows in particular, which are the ones that we're really trying to help the most by using fair queuing, the median slowdown is close to optimal, and the tail slowdown is reduced by more than half compared to the status quo. Now I want to demonstrate how bundler can adapt to varying cross-traffic conditions. So at first, we started with the same emulation experiment, but instead of flow completion times, this time we'll look at the aggregate throughput and delay of the bundle. Now remember, the flows inside the bundle are generated at random. So there are some periods, for example, the first 20 seconds here, where the bundle traffic doesn't saturate the link. And then there's other periods, for example, 20 to 40 seconds, where there's some large flows in the bundle and it is able to saturate. And the important thing I want to point out here is that during these periods, bundler's delay control scheme is able to keep the queuing delay low. Now, in contrast, if we were to briefly compare to the same exact scenario, but without running bundler, since there's no bundler to hold them back, we can see that the queuing delay shoots up as the end-to-end connections compete to fill the bottleneck buffer. And this explains why bundler improves the slowdown compared to the status quo. During these periods, the short flows have a much shorter time to wait in the queue. So now at 60 seconds, we start some buffer filling cubic flows on the same link to compete with the bundle. Using Nimbus, bundler quickly detects the presence of this traffic. And since it has no way of controlling the queues in this scenario, it disables itself. Now, bundler can't enforce its scheduling policy during this time. So if we look at the slowdown at the bottom, we can see that it's no longer able to provide any scheduling benefit, but it does ensure that the bundle retains the aggregate throughput it would have achieved normally. So it's not causing any harm either. Finally, we remove these buffer filling flows, and instead we run some non-buffer filling traffic, which is occupying about half the bottleneck bandwidth. Again, bundler quickly detects that the buffer filling traffic is gone, and it switches back to its normal delay control mode, adapting to the amount of available bandwidth and regaining control of the queuing delay. Since it's now able to control the queues again, if we look at the slowdown at the bottom, we can see that, again, it's able to improve the flow completion times relative to the status quo. So to summarize, bundler is a new middlebox that enables scheduling regardless of where congestion occurs in the network. And it has a simple, lightweight, transparent design, so it's realistic to consider deploying in today's networks. All of our source code and evaluation scripts are available on our GitHub, and we've worked hard to make it easy to reproduce all of our results. So please give it a try and let us know if you have any questions or issues. Thanks for listening.